Welcome everybody to our series on probability and statistics. I am Dr. Lathram, and today we will be discussing the Central Limit Theorem. So let's begin with a statement of the Central Limit Theorem. So the setup is that we have independent, identically distributed random variables, y sub 1, y sub 2, all the way up to y sub n, and we assume that the expected value of each one of the random variables is the same as being mu, and we assume that the variance of each one of the random variables is the same, being sigma squared, and that sigma squared is finite. So if we define a transformation, so first we take the average of our samples, so that's our y bar being 1 over n times the sum of the y sub i's. And then we define a variable u, which is kind of dependent on n, so it's dependent on the size of our sample, u sub n, equal to the average of our samples minus mu divided by sigma over root n. Then the central limit theorem says that as n goes off to infinity, that the distribution of the u sub n's actually converges in distribution to the standard normal. Now, converges in distribution really just means that the distribution functions for the variables converge. And so what this is really saying is that independent of whatever our original distribution is for the y's, if we take a bunch of samples and we average them together from the same distribution, a bunch of independent samples, average them together and subtract the expected value and divide by the standard deviation over root n, then that transformation will end up giving us a distribution that pretty closely approximates the standard normal distribution. So if we stop and think about it, that's really a very, very powerful statement, that it really doesn't matter what my distribution looks like on my random variables. If I do this transformation on them, it's going to look like a member of my Gaussian family, which is really kind of an amazing thing. We go from a distribution that could look like anything, and we end up with something that looks standard normal. So the central limit theorem is probably one of those really powerful theorems that other areas of mathematics where you've encountered those things, things of this nature like calculus 1, then you encounter the fundamental theorem of calculus, you've got the fundamental theorem of algebra, you've got the fundamental theorem of arithmetic, and probably it wouldn't be too much of a stretch to really call the central limit theorem the fundamental theorem of statistics. And so it's a pretty big deal. It's pretty important. So let's see if we can get an idea maybe as to why it might be true. Alright, so now let's do a sketch of the proof. And so we'll define a transformation on each one of our y sub i's to just being z sub I, where we subtract the mean and then divide by the standard deviation. So we have for each y sub I a variable z sub I, which is equal to y sub I minus mu over sigma. Now, it follows from our linearity property, so you can either go back and derive this or check it for yourself, but it will follow from the linear properties of expected value, and that the expected value of each z sub I is going to be 0, and the variance is going to be 1. Now what that tells us is that the moment generating function for z sub I is going to have this particular form for it. So that m of z sub I, so the first term is going to be 1, just indicating that it's a probability distribution. Then the mean is 0. The standard deviation is 1, and so on and so on. Now we don't know what the third moment is, we don't know what the fourth moment is, and it'll turn out that we really don't care exactly what those are. And something else to notice, that how does this apply to our u sub n's? Well, if we take our definition of u sub n and do a little bit of algebra on it, then our u sub n's just end up being a weighted sum, so 1 over root n times the sum of the z sub I. So work through that algebra and confirm that for yourself that that's actually true. Now, our y sub I are independent, and by the form of our transformation from y to z sub I, it's just an affine transformation, so we subtract a constant and divide by a constant. That means that the Jacobian of each transformation is just going to be a constant, and also that the limits in our transformation, just being affine, are still going to go from minus infinity to infinity. So that's not going to change. The limits are going to be independent of one another. And so what that means is that because the y sub I are independent and our limits really don't change, that the z sub I are also going to be independent as well. And so then we recall this theorem about our moment generating functions, that the moment generating function of a sum of independent random variables is the product of their individual moment generating functions. And so what that means is that the moment generating function of our u sub n is just going to be the product of the moment generating functions of our z sub i's. And so we end up with an expression that looks something like this. And so if we take the natural log of both sides, then our exponent comes down in front, and we have the natural log of 1 plus this expression. And so now, again, we think back to some of our freshman calculus and our power series expansion for 1 over 1 minus x to give us the power series expansion for 1 over 1 plus x. And then if we integrate, nice part about power series is we can integrate both sides, and our power series still converge, so we can integrate them term by term. We get the power series for the natural log of 1 plus x, being the expression that we have here. And so what we'll do in our particular case is we will take x to be the remainder of this power series expansion of 1 over 2n to t squared plus blah, 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 blah. And so that's what we're going to substitute in. So that when we make that substitution, we end up with a kind of rather complicated expression that we see here. We've got our x to the first power, our n over 2, x to the second power, n over 3, x to the third power, and so on and so on and so on. And then what we'll do for each one of those n's on the outside, we're going to distribute that inside the parentheses. So the first n just distributes, and we have this expression. The second n, as we bring it in, we take the square root, and so we get an expression where we have an n to the 1/2, an n, and so on in the denominators. We take the cube root into the third term, and so we have an n to the 2/3 in the denominator, n to the 7/6, and so on. For the fourth power, we bring it in and take the fourth root of n, and so we have this, and same thing for the fifth power, and so on and so on and so on. Now what that allows us to do then is, as we take the limit, as n goes off to infinity, any term that has that n in the denominator obviously is going to head to 0. So what that means is that as we take the limit as n goes to infinity of the natural log of our moment generating function, that we just end up with 1/2 t squared. So all the terms go away except for that very first term. And so because exponential functions are continuous, the natural log of the limit as n goes to infinity, the natural log, means that if we apply the exponential function to both sides, that the limit as n goes to infinity of m sub n is just e to the t squared over 2. And that e to the t squared over 2 is the moment generating function for the standard normal distribution. And now we bring back in this fact that we've used multiple times before, that if the limits of a sequence of moment generating function converge, then the distributions converge as well. And so because the moment generating functions converge to the moment generating function for standard normal, the u sub n's will also converge in distribution to standard normal. And so we can see that the central limit theorem is going to be true just because of power series, because of moment generating functions of probability distributions. So we get this really powerful theorem in kind of a natural, relatively simple way. And so now let's take a look and let's go over and maybe apply this to R and see if we can see the central limit theorem in action. So this is a script that I wrote to demonstrate the central limit theorem in R. So let's kind of take a walk through this script. You can kind of see what it does, and then we'll show you the results. Okay, so this is a script written by me. Of course, you can get it on my website, and if you choose to run it, then give me some credit. And of course, caveat emptor, so buyer beware if you use this script. So you run it really by firing up R, going to the directory where you downloaded the script, and type the command source and then the name of the script, and that should do everything for you. And so let's kind of walk through the script and see what it does. So the first command that we see here just clears the workspace of any other variables that we happen to have there. These next two variables allocate space, so they tell R that we're going to have a couple of variables P and we're going to have a variable S. Now P is going to end up being our discrete sample from our continuous distribution that we're going to develop. So what we're going to develop is something called a mixture of Gaussians. And so we will select some Gaussian distributions. We're going to select an interval. And so the left endpoint of this interval is going to be A, and it's going to be out here at -50. The right endpoint of the interval is going to be out here at 50. And we're going to take this interval and we're going to divide it up into 1,000 subintervals. And so that gives us a width of each interval of dt being b minus a over capital N. So for our discrete probability distribution P, we're just going to take our interval from -50 to 50, divide it up into subintervals, and those subintervals will be the values of our discrete probability distribution. S will be representatives from those subintervals, and that will constitute our sample space. So what we'll do now, so for the central limit theorem, it says that for whatever distribution we choose to make, that we can, as we increase the size of our distribution, so we increase the number of times from which we sample from that distribution, then if we transform it correctly, we will get something that looks like standard normal. And so in this case, I'm choosing a value of n, and so what n is, it will be 100 samples from this particular distribution. Okay. So now let's go down and look at this loop a little bit. So we're going to loop through, and we're going to construct 30 different random Gaussian mixtures. Okay, so how we do that, so the Gaussian distributions take two parameters. They take mean, and then they take a standard deviation. And so what we're going to do, we're going to randomly select from a uniform distribution from between -30 and 30. We're going to select 11 means. So this is our mu.given. We're going to select standard deviations, 11 of those from between 0.1 and 4. Okay. Then for our mixtures, essentially a mixture model is nothing more than a weighted sum of other distributions. So what these two commands are doing here is picking our weights for our distribution. So again, we take here, we've got 11 numbers from a uniform distribution between 1 and 10, and then in order to get a probability from that, we just add them all together, divide by our total, and we've got a value for weights for our mixtures. Okay, so then what these next few lines do, we are picking elements of our sample space. So we're going to have one representative for the interval to the left of, so from minus infinity up to negative 50. So we're going to have a representative for that, and that's what this value does. And then we calculate the probability density function, so the CDF. So we calculate the cumulative probability for all of our models, given our means and given our variances for our left endpoint, and we scale that by our weights, add them together, and so we get a probability for our left endpoint. Now in between minus 50 and 50, we are going to pick our representatives. So our representatives are basically going to be our right endpoints. And then we will do the difference of the cumulative distribution functions for the right endpoint minus left endpoint. So we get the probability of our Gaussians by actually being in that interval. And then, of course, we scale that by the weights, add them together, and we get our probability for that particular interval. Then we do the same thing for everything bigger than 50. So we'll take our representative of b plus dt over 2, calculate the upper tail for our Gaussians, weight them, add them together, and we get our probability for the upper interval. And so this will give us a discrete sampling of our values between for essentially the entire real number line. And we have a discrete probability from that, from our Gaussian mixtures. So to draw a picture of that, this is what these next few lines do. So these values will draw a plot of our density function. We'll save that. And then we'll calculate what the true mean and the true variance will be for our discrete probability distribution. Then, now here's where we run our samples. So we will sample 100 times. So that's our value of n. So we're going to take n to be 100. That we're going so that we get a reasonable distribution of u's from this. Well, then we'll actually get a sample of 500 of the u's, where u sub 500. So we're gonna, or a u sub 100, where n is going to be 100. So we'll get a sample of 500 u sub 100s, and that's what we have here. We'll get our sample of 100 of them. We will average them, subtract the mean, divide by standard deviation over root n, and then we will draw a histogram. So we'll draw a histogram of those values so you can see, well, here's what the histogram is going to look like, and then we will overlay that with the probability density function for standard normal. And so hopefully for seeing the central limit theorem in action, what we should see is that this really strange looking probability density function on one graph, and then the next graph we will see something that will hopefully look standard normal. So we can fire up R, go through those, and let's take a look at some of the results. So what you're seeing here is the sequence of graphs generated from our script that we just walked through. First you see a particular probability density function. So you see the graph of something that's a density function. It's a mixture of Gaussian distributions. And from there, we divide up our interval between minus 50 and 50 up into subintervals, compute the cumulative distribution function for each one of the subintervals, and that becomes the discrete distribution from which we sample. That script is available on my website at sites.google.com/site/glathram271. If you go to the teaching tab and probability and statistics, you'll be able to find that script. And so the next graph in our pair is a histogram that's taken by sampling 100 times from our discrete distribution. We then take the average of those 100 samples, subtract the mean, divide by the variance, do the transformation prescribed by the Central Limit Theorem, and then we do that a total of 500 times to get a distribution of the U sub 100s from that. And then what you're seeing there is a histogram of those U sub 100s. So in the histograms themselves, you see the PDF of standard normal overlaid with the histogram, and we can see that, yes, sure enough, we do get a pretty good approximation from our histograms to the standard normal. And so that gives us an application, a real life viewing of the Central Limit Theorem in action. And so now we'll end the video by going back and kind of doing the same thing, but instead of using Gaussians, we'll go back and use members of the gamma family. So these will be a mixture of gamma distributions. And so the same thing, we'll randomly select a bunch of gamma distributions. We'll randomly select parameters, weighting values to get the mixture, and then show you the graph of the PDF along with then the histogram when we sample, and we can again see the Central Limit Theorem again, not just for a mixture of Gaussians, but also for a mixture of gamma functions. And so that's the key thing, that it really doesn't matter what family you choose, you're always going to get something when you sample and transform in the right way. You're always going to get something that looks like standard normal. And that's why in most situations, sometimes people will just automatically assume, oh, I'm sampling from standard normal distribution. We shouldn't probably assume that you're sampling from a standard normal distribution, but in the process of sampling and when you transform correctly, you do get something which does resemble standard normal. So I hope you've enjoyed this video. So check us out if you want to review some old things, what the gamma distributions are, what the Gaussian distributions are. Check out our other videos, and I will see you all next time.